Welcome everybody to the second session on mixed models. Please make sure that you've gone through the material for mixed models part 1, because in this session we'll be building very much on what we covered in that first session. Okay, so just to kind of recap where we're up to and to give you a bit of an oversight into what we're going to cover in this session. So previously we looked at how mixed models are related to, but more flexible than models built using the general linear model. And I guess in terms of the research that I conduct myself, the advantages of mixed models are that you can model multiple random effects simultaneously. So that means you can account for the fact that your subjects are all a bit different from each other, and you can account for the fact that your experimental items are all a little different from each other. So you can model these kind of random effects. And another real benefit from my perspective with respect to mixed models is the fact that you actually are building your models over your individual data points. So you're not aggregating your data and building models over averages, which is what you do when you're conducting ANOVA or building models based on the general linear model. But with mixed models, you can build your models over the actual data points themselves. You're able to account for the lack of independence in your data via your mixed models, which means that you're using a lot more information that's in your data set to actually build your models. So last time we looked at mixed models for designs involving one experimental factor with multiple levels, and we looked at the kinds of random effect structures that we could build to kind of capture the variability between participants, the variability between items in our data set. We also spent a fair bit of time looking at how we interpret the results of mixed models, and also critically how to test whether the assumptions underlying our mixed models have been met. So we're going to kind of build on all of that stuff in the present session. So we're going to look at mixed models for factorial design, so that's when you've got multiple experimental factors, and you might be interested in how the factors interact with each other. We're also going to look at mixed models for cases where our outcome or dependent variable isn't continuous. So we're going to look at cases where we've got binary outcomes, and we're also going to look at cases where our outcome variable is ordinal, as might be the case if you're collecting Likert scale data, which is very often misanalyzed. You shouldn't really be using analysis of variance to model Likert scale data. You should be building ordinal models to do that. So this is the first thing we're going to look at. It's a mixed model for a design where we have two experimental factors, each with two levels. So 2 by 2 repeated measures design. So that means we've got 4 conditions, and each participant sees items from each of those 4 conditions. The first factor is context, whether the context is negative or positive. And the second factor is sentence type, whether sentence type has got a negative or positive meaning. So, excuse me. So basically, people are reading sentences in context. And the idea is that if the context is quite negative, people might then be faster at reading a subsequent negative sentence in that context, relative to reading a negative sentence in a context which had actually been positive up to that point. So you can kind of think of this as a little bit of a priming type effect. So our dependent variable is reading time duration to the target sentence. So overall, we have 60 participants and 28 items. And here's just the first 6 rows of our data set here. So we can kind of see subject item, reaction time, context, and sentence. And we can see that things are already coded as we'd like them to be. So we've got subjects and items coded as factors, and our 2 experimental factors, context and sentence, also coded as factors. So we can ask to use the str command, structure function, to explore our table in a little bit more detail, and we say that for context and sentence, we do indeed have the two levels of each of those factors coded. So one of the first things it's always a good idea to do when you're going to build a model is actually generate some descriptives and plot a visualization of your data. So we're going to do now exactly the same sort of thing that we did in the first part of the mixed models session. So we're going to generate some descriptives. So we're taking our data frame, tidied factorial data, and then we're going to group it by context and sentence, i.e. our two experimental factors. And then we're going to ask for summary statistics, such as the mean reaction time and the standard deviation of the reaction time. So just very basic descriptive statistics. Now, something intriguing happens when we run these 3 lines of code. This is the output down here, and we actually see 4 NAs, telling us that there is a slight issue with our data set, likely to be missing data. Now, one of the great things about R is that if you have missing data in your data set, it won't decide what to do with it. It'll actually flag it up as an issue, as it's done here, and you have to make a decision as to how you want to deal with the missing data. Okay, so we might want to explore just initially how much missing data we have and where it is. So we're going to use a great package called visdat. Visdat has got 2 functions in it which are very useful. There's visdat, the function, and vismiss, the function. So we simply pass our data set, tidied factorial data, to visdat, and we get this nice visualization here. We're given the 5 columns in our data set and what type they are. And interestingly, down here we can see we've got some missing reaction time data. So we can explore that in a little bit more detail using the vismiss function, and we are told that we have some missing data here. So we can see we've got about 0.1% of our data are actually missing. So that's a nice way to quickly visualize our whole data set and help us understand what might be going on. So we now need to just modify our piped commands to filter out the missing data. And there are several ways you can do this. The way I'm going to do it is by taking our data frame, tidied factorial data, and then I'm going to filter out cases where we don't have missing data. So we're basically applying this line here, and this is going to effectively exclude those rows where we have missing data and pass through to the pipe here only cases where we do actually have complete data. And then we're going to group by context and sentence, and then we can generate our summary statistics in exactly the same way. So because at this point we don't have any missing data because we filtered it out, we don't have any problems down here. So we get our mean and standard deviations of reaction times exactly as we'd expect to see. So we filtered out our missing data to do that. It's always a good idea to build a visualization as well to give you a feeling over what kind of what your data look like, what sort of distribution shape your data follow. So I've done a few things here to produce a plot of the individual data points. I've added a violin geom to give us the shape of the distribution, and I've also added a black square for each of our 4 conditions corresponding to the average for that condition. So it's a good idea, again, just to kind of visualize your data before you build any model, to give you a bit of a feeling as to what your data look like, what sort of distributional shape they follow, but also you can have a wee look to determine whether or not the effects that you're predicting are actually likely to be uncovered by the model you're going to be constructing. So if you recall, we decided, or we predicted, that negative sentences were likely to be read more quickly in negative contexts than positive contexts. So down here, we've got negative sentences in negative contexts. Here, we have negative sentences in positive contexts. And if you just look at the difference between the average for these two, you can see that this reading time here does indeed seem to be a bit slower than reading time down here. And we can look at that in the descriptives as well. So we've got 1474 versus 1633. So there does indeed seem to be about 160 milliseconds between those two conditions. In contrast, if we look at positive sentence reading times in positive contexts versus positive sentence reading times in negative contexts, visually at least, there doesn't seem to be a huge amount of difference between those 2 points. And we can look here and we can see that actually, it's only about 16 milliseconds. So we kind of think, well, actually, there does seem to be a little bit of a possible priming effect going on here, but it's not symmetrical. It seems to be driven by reading times to the sentences containing negative information. But we need to build our model to determine whether or not that's kind of a statistically supported conclusion. So when we're building models for factorial data in R, we need to be quite careful because R, by default, codes our factors using dummy or treatment coding. So if you recall back to the ANOVA lectures, and when we were looking at ANOVA as a special case of regression in the context of the linear model, we actually used this kind of dummy or treatment coding to actually build that model, where one level of our experimental factor basically acts as the intercept of our linear model that we're building. So by default, R uses that kind of 0,1 coding scale, which actually is problematic for mixed models with interactions. So if we were to use the default coding scale in R for building our mixed models, that will actually make it harder for us to interpret our parameter estimates, but also critically, it can result in misinterpretation of main versus simple effects. So in the Markdown document, I've added a link to a really great paper that came out in the Journal of Memory and Language recently, which actually delves into this in a lot more detail to kind of show you what the issues are and what the sort of pitfalls are associated with using the wrong sort of coding scheme for your different factors. And interestingly, many published articles either get this wrong because they don't use the right sort of coding scheme, or actually they underspecify. They don't actually tell us what coding scheme they use when they're building their model, which is hugely problematic from a reproducibility point of view. So rather than using the dummy or treatment coding that we get as default in R, we're going to use what's known as sum or deviation coding. So the paper explains this in a lot more detail, but basically what this means is that we end up with a mixed model where the intercept of the overall model is equal to the grand mean of our conditions. In other words, the intercept of our model is equal to the average of all our different experimental conditions. And that makes it a lot easier to interpret the parameters in our model, and also means that when we're interpreting main effects of our different experimental factors, they really are main effects rather than simple effects. So it's important from that point of view as well. And the way we're going to set up our contrast is relatively straightforward. We're going to use these two lines of code here, setting up the contrast separately for two experimental factors using this coding scheme down here. Okay, and ultimately what this means is we end up with the intercept corresponding to the average of our 4 experimental conditions. So we set up our contrasts, and we simply then build our model very much in the same way that we did previously. Now in this case, we've got our fixed effects here. It's written as context, asterisk, sentence. What that actually corresponds to, if you want to unpack it, is this expression down here. The main effect of context plus the main effect of sentence plus the interaction between those two factors. So this is really just a shorthand way of writing out this down here. So we've got our fixed effects, and then we're going to model our random effects, such as we've got a random effect of subjects and a random effect of item. And initially, at least, we're going to try and model these random effects such that we're expecting our main effects plus the interaction term to differ for each of our participants and also to differ for each of our items. So we're building what's known as a maximal model where we have intercepts and random slopes for all of our fixed effects terms. Okay, so that's kind of the model we're going to try and build initially. So if we were to try and build that model, we'd actually get a warning message. And the warning message tells us that it couldn't converge on a solution of a model that fits our data set. So very often this can happen when you're trying to fit a more complex model to your data set than the data set actually allows you to fit. So maybe you don't have enough observations, for example. So one way to kind of address this issue is to simplify the random effects structure in our random effects terms until we find a solution of a model that fits our data with the right sort of parameters that can be estimated that we're looking for. So what I'm going to do down here is simply drop the interaction term of context by sentence for our subjects. We've now we're going to model just the main effects of context and sentence as the random slopes for our subject random effect term. So we're going to drop that, and it's a good idea to drop random effects terms on the basis of the amount of variance they explain in the data. So if you were to look at sort of the model that failed to converge, you'd find that the variability accounted for by the subject random effects term is actually less than the item random effects term, so we can maybe then decide that we're going to simplify the subject random effects term first. So if we do that, we actually get a model that fits. So what we want to do first of all, before we really delve too deeply into understanding what the model parameters actually correspond to, is just check some of our assumptions here. So we've got assumptions related to multicollinearity. So we see that the correlation between our experimental factors is low. We've got a couple of plots that tell us about normality or non-normality of our residuals. And it's kind of interesting because this is looking pretty good to me up to about the 2.5 second mark. At about the 2.5 second mark with our data, the normality of our residuals seems to drop off. So our model is pretty good up to that point. So it seems to be the tail of our distribution is causing problems. We also get information about the normality of our random effects by subjects and by items, and they look pretty good as well to me because we're expecting the dots to follow the solid sort of turquoisey line. So let's move ahead now and bear in mind that we might have a slight issue over the non-normality of our residuals. Let's actually start to interpret the output of our mixed model. We're going to do that in the same way that we did last time, using the means function in the means package. So we're going to pass to the means function our factorial model. We're going to ask for pairwise comparisons based on the main effects and interaction of context by sentence. And we're not going to adopt any adjustment. We don't, in this case, necessarily want to cheeky or Braun-Ferroni adjustment because there are multiple comparisons that we're going to be making. Only a fraction of those comparisons are going to be theoretically meaningful. So we can actually do the adjustment ourselves. We can do a Braun-Ferroni adjustment ourselves by multiplying the calculated p-value by the number of sort of theoretically sensible pairwise comparisons that we're going to make. So the only theoretically sensible pairwise comparisons are ones we're comparing like with like. So in other words, positive sentences in positive contexts versus positive sentences in neutral context, or negative context rather. So that's one sensible comparison. And then negative sentences in negative contexts versus negative sentences in positive contexts. So there are only two sensible comparisons that we might sort of be making. So we can multiply the calculated p-value that we get by 2, and that's basically doing the Bonferroni correction manually. So if we look down at the pairwise comparisons, we see that the only one that's significant, and this is consistent with what we saw in our visualization, is the one where we've got negative sentences read in negative versus positive contexts. So we see there's a difference about 153 milliseconds between those two conditions. The last line down here corresponds to the positive sentences in positive versus negative contexts, and there's nothing going on here. So the p-value that we calculate is 0.0061. We should be multiplying that by 2 to correct for the fact that we've made multiple comparisons, and there were two theoretically sensible multiple comparisons to make. So our p-value that we'd report would be 0.0122. And we can look at our descriptus and our visualization, and again it just supports what our model is telling us. This point versus this point is significantly different, whereas this point versus this point is not. And again, we can just inspect the descriptive statistics and see that that is indeed the case. So we can look at the parameter estimates of our model itself, and we can see we've got this significant interaction effect of 0.0417, which we then unpacked using the EM means comparison on this slide. And actually, I should have really said we examined the model parameter estimates before we would do any EM means comparison, because if this interaction down here hadn't been significant, then we wouldn't have been justified to look at those pairwise comparisons using EM means. We've got a significant interaction effect, and it's being driven by negative sentence reading times in negative versus positive contexts. And we'd write up the results something like this. So it's really important to remember when you're writing up the results of any analysis in R that you provide sufficient information to allow a reader to fully reproduce your results. So it's important to specify the packages that you've used, the version of R that you've used, and it's also important to cite those packages as well and make it very clear sort of any assumptions you've made or any procedures you've used to analyze your data. Again, simply it's all about being transparent. Being transparent is about giving the reader all the information that they need in order to make the results section entirely reproducible by somebody else. So as I said, it's really important to report the version of R and associated packages. And you can actually get the list of packages that you've used plus their version numbers by using the session info function, which will actually then generate in the console all the packages and the version numbers of those packages that you've used. In virtually, all cases of decent journals these days, when you submit a paper, they also ask for you to submit your analysis code and data. This is the world of open research and reproducibility. It's very much changed. It's very much changed and is continuing to change the publishing landscape. And if you think back to that very first session where we talked about the so-called replication crisis and issues around reproducibility, you'll understand just how important this level of transparency actually is. And one of the best ways to ensure reproducibility is to use a tool such as Binder, which you can learn about in more detail in one of the other workshops that you can access. So you really want to make sure that everything we do in terms of the analysis is fully reproducible by reviewers and readers of our journal article. I just want to spend a minute or so now talking about one of the common issues that you're going to come across when you're building mixed models. It's to do with these convergence errors, where the model isn't able to settle on a stable solution to provide you with the sort of parameter estimates you're interested in. And what that means is that you're probably trying to estimate too many parameters than your data will actually allow you to do. In other words, your data set isn't rich enough to support the complexity of the model that you're trying to build. And what you need to do is simplify the random effect structure in order to be able to build a model that can kind of provide those estimates that you're interested in. And as I mentioned earlier, one way to do this is simply to simplify the random effects terms that explain the least amount of variance in your data set. And you can check this using the summary function. So you can have a look when your model doesn't converge using the summary function to see how much variability your different random effects terms explain, and take the term that explains the least amount of variability in your data and then simplify the random slopes within that random effects term by doing things like dropping, say, the interaction term first of all. But it can be quite tricky. There's many cases where you will probably have to simplify your random effects terms, and one of the issues is that if you end up with random effects terms that are too simplified, in other words, they only have random intercepts, they don't have any random slopes, you end up with a situation where you're actually inflating type 1 error rate. In other words, the possibility that you're finding a false positive. So it's really, you have to be careful about simplifying too much because you can end up with a false positive. In other words, thinking you have an effect in your data when one isn't actually present. One of the many great things about mixed models is you can add multiple participant and item covariates simultaneously as fixed effects. So it's a good way of modeling individual differences between people and items. In language research, maybe you could covary out something like lexical frequency or word length or something like that. You can have a whole range of both continuous and categorical variables in your mixed model because they're very flexible. But what's interesting is that sometimes you can find several models that fit your data, and what you can do is then run the likelihood comparison test on the nested models to determine which is the best fit. And this is something that we spent a little bit of time looking at in the previous session. But if you have a selection where it's not the case that one model is statistically better than the others, don't get too carried away with focusing on the kind of model comparison using these statistical comparisons. Remember, at the end of the day, in your research, you're working within a theoretical framework, you're examining a specific research question contextualized within that framework that hopefully makes very clear predictions about what you're likely to find in your data. So it's important to ensure that when you're building models, you're actually guided by this broader theoretical framework, and you actually choose the model that makes most theoretical sense in the context of the framework within which you're actually working. So we've looked at a case where we're kind of assuming that our data distribution that we're modeling is roughly normal. We had a bit of a issue when we looked at the model assumptions, and we seemed to find that the normality of our residuals fell off at some extreme values. It was values over 2,500 milliseconds. So it may be the case that although we're assuming we're sampling from a normal distribution when we build our model, that may not be entirely true. There's a great package called visdat plus. I think I've actually spelled that wrong up there. I'll correct that in the slides. which has a function called deskdis for describing a distribution. And you can use that function and it will plot on what's known as the Cullinan-Frey graph where your data actually lie. So our observed data are going to be indicated by this little blue circle here. We've got lots of different types of data distributions plotted on the Cullinan-Frey graph. So anything in this grey area here follows what's known as a beta distribution. The normal distribution is indicated by this asterisk here. The uniform or flat distribution by this little triangle here. Logistic distribution is about here. And then we've got log normal and gamma distributions indicated by these lines. So let's look on this graph where our data set is actually plotted. And we actually find that our data set, as indicated by this blue circle, is actually way down here. So it's quite far away from where the theoretical normal distribution is. And actually it's pretty close to what's known as the gamma distribution. So let's just have a quick look at what a gamma distribution actually looks like. And it looks a lot like this. So we kind of see it's kind of a skewed normal distribution. And interestingly, when you think about reaction time and reading time data, very often the distribution of the data you collect is going to look quite a lot like this. There'll be a point below which you don't really get any reaction times or reading time measures because people's eyes don't move quickly enough, people can't respond quickly enough. Then you get quite a cluster of points round about here, and then you get a number of trials and people who are just a bit slower. So you get this extended right tail. So this is a fairly typical gamma distribution. And what's interesting about the gamma distribution is that very often reaction time data follow the gamma distribution. Traditionally, what researchers might have done is transform their data set. That's something you should never do. It's kind of the sort of old way of trying to handle this. But there are actually a number of more recent developments in terms of model building, especially in the context of mixed models, which actually allow us to build a model that assumes that our data come from something like a gamma distribution. So we can actually build what's known as a generalized linear mixed model, and we actually specify that the family that we're sampling from is the gamma distribution. And in the markdown, I'll actually work through what we would do to build a generalized mixed model, assuming sampling from the gamma distribution to model the reaction time data that we just looked at there now. So there are a few caveats really just to say at this point. Gamma mixed models are often harder to fit, and frequently what you need to do is really simplify the random effect structure in order to find a model that kind of converges with the parameter estimates appropriate for your data set. What I tend to do, and always think of that George Box quote, all models are wrong, but some are useful. I tend to fit different sorts of models to my data set, because assuming that all those models are appropriate. And if the same basic story emerges, whether I'm fitting a straightforward linear mixed model or whether I'm fitting sort of a gamma generalized linear mixed model, if the same story emerges regardless of my model choices, under the assumption that all those model choices are largely appropriate. So if the same story emerges, then I can be pretty confident that the effects that I'm uncovering are there in the data and ready to be and waiting to be uncovered. I think it would be more problematic if effects came out strongly under one model, but were completely absent under another model. Then I would worry that those effects really weren't actually there and they were coming out because of some quirk in terms of one of the models that I was building. So it's a good idea to build different sorts of models to try and model your data. And if the same story consistently emerges in terms of what's significant or what effects are driving your model, then you can be pretty confident you've actually got those real effects in your data set. There are a couple of great papers I'd recommend that you have a look at if you're interested in understanding a bit more about why we should be using, say, gamma distribution for your action time data rather than, say, log transforming our data. This one down here, the frontiers in psychology one, goes into that in quite a lot of detail. So just to finish off this session, before we move on to the next video, so you're going to find cases where you're trying to fit a model with too many parameters, and this is where you really don't have a rich enough data set. So simplify your random effect structure. Often you're going to start by removing random slopes associated with your interaction terms if you've got a sort of factorial design, but try to do it in a way that makes theoretical sense, that fits your data. It can be really difficult because very often it's a judgment call on your part as to how to simplify your random effect structure. And my general advice would be transparent. At the end of the day, be transparent in all of the decisions that you're making when you're analyzing your data, because transparency means that somebody else will be able to reproduce your results. And that's really important in terms of open research and reproducibility. And if you're interested in reading more about mixed models in general, how to simplify the random effect structure, in addition to the paper by Dale Barr I mentioned earlier, there's also this nice one by Doug Bates on parsimonious mixed models. Okay, so that's the end of the first video. So if you'd like to now work through the next section of the Markdown document before we move on.